right, hi. Thank you all for being here today to listen to me gab a bit. So let's see here. Okay, yes, works. All right, so yes, my name's Jacob Turner. I'm an engineer at Helix. And today I want to talk to you a bit about something that I've worked on quite a bit, and that is front-running protection that we've got planned for Anoma. So, first thing we should probably make sure is we're all on the same page is what is front-running? So, I mean, maybe you all know, but I'm going to tell you all anyway. So, in our in a normal blockchain, we normally have a transaction that comes in. In this case, somebody wants the user wants to buy a CryptoKitty from Bob. Right, this just gets submitted into a large waiting area of transactions, and then from there, some lucky validator gets chosen to create the next block. They pull out this transactions from the mempool, and they submit this block proposal. Right, the problem, of course, comes from the fact that this validator can see all of the potential ways that the market can move and has some control over this. So this, I mean, if you can see how the market's going to move before it moves and have some control over this, right, we all know, Martha Stewart knows very well, for example, and that you can maybe make some money off of this. So you have some inside knowledge, and generally this is not considered a good thing. So some blockchains have this problem quite a bit. It goes by various names. Miner extracted value, is another term it goes by. And you may censor transactions you don't like. So for example, if this validator really wants this CryptoKitty, they could just decide not to include your transaction because they're like, nope, I want that for myself. So you have censorship of transactions. You have the potential to reorder transactions in some way that might be advantageous to you as a validator. Or you might craft your own transaction and insert it in between two existing ones in order to make some sort of a trade and pocket the difference in money. There's various things that can happen here. So we want to prevent this, right? Really, a validator should help secure the chain. It should not know about the market and before it happens. So really there's sort of two fundamental things here that make this a problem. Right? So first, the block proposer has considerable control over future state changes, right? They get to choose what transactions go in, which transactions don't go in, and what order they go in. And on Anoma, the order of transactions matter. There are some chains out there that somehow manage it so that transaction order doesn't matter, but for us, that's also an issue. And the second thing, of course, is that they see all the ways that the state could change before it changes. So there are sort of two different sides to this: the control aspect and the really seeing state changes before they actually seeing the future, essentially, or the possible futures. So various blockchains have tried to come up with solutions to this problem. Some sort of attack this first point here. So you try to restrict control on the kind of proposals that are allowed. So some chains have adopted this. So for example, perhaps you don't rely on a single validator to create a block proposal. So maybe you have several validators who get together and they somehow have some collaborative means of creating the next block. That way, since you don't have a single person, it's much harder unless all the people involved in the proposal are colluding, which, it becomes much harder then to create a block proposal that will in some way really benefit you and to do this kind of front running. This is not really an option for us at Anoma. At the moment, the simple reason that we are using Tendermint's consensus algorithm, which uses a single validator to make block proposals. And this is really quite a big limitation on any consensus we might want to consider in the future. There are many consensus algorithms that we would like to be able to consider where we only have a single block proposer. So this is not something that we decided to go for because, well, yeah, for those reasons. But there's other things that we can do. You can try to, of course, use some deterministic rule or some source of on-chain randomness. This is mostly solving the problem of ordering transactions in some advantageous way. So here you try to take the ordering of transactions, take that control away from the block proposer. Something simple it could be as simple as let's hash all the transactions and order them alphabetically. But this doesn't, and this is something that, I know we might do at Anoma, but of course it doesn't solve all the problems. It doesn't solve the problem, for example, of censorship, where you just decide to simply not include a transaction that is disadvantageous to you as a block proposer. So these are partial solutions, but we are really more focused on that second bullet point. So block proposers see all the ways the state may change before it's changed. This is where we are really going to try and attack the problem head on. And the idea is simple. We just make it so that you can't see what's in a transaction. So solution 2 is to, like I said, try to prevent this knowledge ahead of time, this foreknowledge. So here we have the same transaction, but now we're just going to encrypt it, right? And once it's encrypted, it then goes into the mempool. So when you are a block proposer, you will not see the transaction by CryptoKitty from Bob. You see some opaque encrypted blob. So you don't know what the future will be at this moment because, well, it's encrypted. So the idea now is that we have an encrypted mempool. All the potential transactions that block proposers are going to be working with at first are going to be encrypted. So this it makes it much harder for them to try and censor transactions they don't like, order them in some advantageous way, et cetera, et cetera. But we still have to eventually get these things on chain and execute them. So we use a commit and reveal scheme. So at first what we do is we have this encrypted mempool, and a block proposal will work the same way. The block proposer will go grab off from its mempool a series of transactions, and they're all encrypted. But we go ahead and we gain consensus on this block of encrypted transactions, right? So we make a proposal, all the validators sign off on it, we finalize the block. And now what we've done is we've committed to which transactions will be in the block and in what order they're going to be done. It's very easy to do hash checks to see that if I see an unencrypted transaction, what encrypted transaction it will correspond to. So then we decrypt, and in the next block, we put in the exact same transactions and do the necessary state changes in the order that we committed to at block N. So now we have a 2-step process for committing state changes. At block N, we gain consensus on how the market will move, and at block N+1, we reveal what that is and actually make that take effect. So this is really a commit and reveal scheme. Now this all sounds great, of course, except that, how do we encrypt these things? How do we decrypt them? I mean, we can't just have a decryption key lying around somewhere because obviously people would decrypt them and figure out what's in these transactions before they're supposed to. It's really important that we only know what's in these transactions. In this case, at block N+1. At block N, these should be completely opaque, or as opaque as we can get them to validators. Unfortunately, it's really hard to make these things completely opaque, but we want to hide as much information as we can. So the idea is really that we're going to so the idea is we're going to use threshold decryption. And simply, the way I like to think about this is that instead of having one encrypted lock, we have, you can either think of it as a lock that requires multiple keys, to unlock, or multiple locks and everyone has it, and all wrapped around each other, and all the validators have to remove all the locks before the thing will open. So the way this will work is that we have a transaction, it's encrypted, and only when 2/3 of the validators get together with their keys and combine them together are we able to actually open the transaction and see what's in it. So no single person has access to the decryption. It requires, in our case, 2/3, or any. In theory, you would always want to tie that to the same amount of validators needed to gain consensus. And we actually tie this to finality. So it's also really important that if we commit a block, we should be able to decrypt things. If they're correctly decryptable. Obviously, if something goes wrong, won't be able to decrypt. So so I'm just going to say a little bit more about this, and then at the end, I will actually very quickly do some math. If you don't like math, you can tune out at that moment. It's only 2 slides, and it'll be quick. So so the general flow then is this. We publish some sort of public key. Users use this to encrypt their transactions. We then have a completely encrypted mempool. We first then gain consensus on the transactions to be included and their order. Then validators, when they're voting, actually at the exact same moment they're voting on the block of the encrypted transactions, will submit with their vote their bits of the key that will then allow us to decrypt these. So that at the end of committing to this block of encrypted transactions, we have all the information needed to actually decrypt them. And in the next round, we then take their decrypted counterparts, and that should be the next block proposal. And of course, if it isn't, and some block proposer tries to cheat, we reject this block, and someone else gets the chance to be the block proposer and get all the nice rewards that come with that. So this is the overall commit and reveal scheme. So then how do you actually do threshold decryption? So trigger warning math. The idea is actually pretty simple at a high level. Of course, the decryption key is going to be based on some sort of polynomial. Usually we have a deterministic way of taking the constant term of this polynomial and turning that into something we can plug into cha-cha to encrypt and decrypt. And the nice thing about polynomials is that a polynomial of degree n, right, is uniquely determined by how it is evaluated at n+1 points. And if you have these n+1 evaluations, you can share them, right? So this allows us to share, to split up the necessary information amongst different people, up to n+1 people. And then, so this is how you effectively split up a key. Right, so yes, these are split up among validators. In our case, we'll choose the polynomial to have degree 2/3, so that if we get strictly more than 2/3 of the validators, they can reveal their evaluations. We can use Lagrangian interpolation to reconstruct the polynomial, grab its constant term, and get the key that will decrypt our transactions. Right, and a crucial thing about this is that when we vote on a block, a validator must include their evaluations. So this is really tied to finality. We really don't want to get into a case where we've committed to a set of encrypted transactions and didn't actually get the the means necessary to decrypt them. So that's an important point. And then the distributed key generation. What this is of course, how do we actually generate the key that we will use to encrypt these transactions? So, like I said, it comes from this polynomial. How do we create a polynomial that nobody knows? So that's sort of the second key bit of the puzzle here. The idea is actually pretty simple. We just have every validator create a polynomial. Now, every validator, of course, knows the polynomial they created, but then what do? We can encrypt the coefficients of this polynomial, and we add the encrypted things all together. So by summing up all of these polynomials, we end up with a polynomial that nobody knows. Everyone knows one of the summands that goes into this polynomial, but since they don't know the others, they don't know the result. And so, yes, the result is some encrypted polynomial that no single validator knows. And from that, you can publish a key that users can use to encrypt their transactions. So, and that, I promise, is the end of the math. So, at this point, I was wondering if there are any questions. Yeah. I think it is, no, it is not, I would say, entirely novel. Yes, the question was, is this method novel for making distributed key generation? And the answer to that is that versions of this have existed before. Of course, what's novel is tailoring it very much to our sort of blockchain context. But the idea of like doing, having a group of people do some sort of distributed computation so that the result is not known to every party at first, ideas for doing that have existed in the literature for quite some time.
Hi. What kind of like sensible, reasonable ceilings do you think exist for like number of participants in the DKG scheme that you have?
So we've tested up to less than 200. There is a real scalability concern, especially because we're using groups with elliptic pairings, and those are quite data heavy. Since we're using Tendermint consensus at the moment, which uses all-to-all communication, that is quite a lot of data to be passing around. So far, it seems, so I think we normally use around, in testing, we use a very small number of validators, and the feature is almost complete, but not quite there yet, so we don't have good benchmarks on what it looks like in practice. There are some aggregation tricks that we have that might be able to speed this up if we need it, but that we're still in the testing phase to figure that out. Interestingly, a lot of the time actually just comes from simply marshalling and unmarshalling the data as well. So it's something we're still in the midst of figuring out.
Can you comment on how the ordering of these encrypted transactions in the mempool is determined by the validator?
So in the mempool should be considered not ordered. It's generally the way, of course, it's implemented in practice is that as you receive encrypted transactions, you throw them into your mempool in that order. There's no guarantee of what order that will come in, obviously. And then you just grab the top off until you maximize out your block by whatever the size limit is. So in practice, that's how we do them, how the ordering will be done. Of course, if you can see the transactions, which is how many blockchains do it, validators then try to reorder them to their advantage. But here, there's very little incentive to do that. But yeah, the mempool, there's no, it should be thought of as unordered, and due to the fact that it's a distributed network and it's all asynchronous, that introduces randomness into this ordering. So it's hard to predict. If you know what users are doing, what order you're going to actually see them land in your mempool.
Okay. And do you also mind if I ask one more question?
Oh, go ahead.
So, also when trying to decrypt this, so this 2/3 kind of consensus for decryption, is it like 2/3 of the validators are always selected to participate in this process, or like can 100% of the validators?
Definitely all of them. We just need, so it, really well, let me try to stay on my feet. Yeah, so of course it's called threshold decryption. So as soon as we meet the threshold of 2/3, we can reconstruct the key. If we get 100% of validators, great. We can also decrypt the transaction. And of course we expect that most of the time we'll get way more than 2/3. But the key thing, right, is that if we have a polynomial of a certain degree, if we get more evaluations than we need to reconstruct that polynomial, we're in business. So it's really not a problem. We just need 2/3, and then we can reconstruct the polynomial and get the key out.
Okay, so well, like, does that mean that you are always choosing a polynomial that has degree equal to 2/3 of the validators?
That's correct.
Gotcha. Okay.
So actually, and there's a detail here. We have a pipelining for our validator sets coming in. Validators, before they become actively validating in the epoch before, they're in the pipeline, so we know how many validators are going to be. We ask, and it's mandatory at that moment for them to go ahead and submit the required data so that they can get their keys can be distributed to them. So we know all of this ahead of time. So we have a pipeline length of 2 epochs precisely so that we can get this set up before they actually start the work of validating the network.
Gotcha. Thanks.
Okay, well, if there's you have any more questions, of course, feel free to talk to me afterwards, but I think it's time for me to hand the mic over to the next speaker. So thank you again.